Hello and welcome. In this notebook, we cover Introduction to Design Patterns, Creational Patterns, and Structural Patterns as the Part 1 of Design Patterns video. Please like, share, and subscribe to support this channel. Introduction to Design Patterns. What are design patterns? Design patterns are reusable solutions to common problems that software developers face when designing systems. They are not specific code snippets, but general templates or best practices for solving recurring issues in a particular context. Think of them like blueprints that can be applied to different programming scenarios. These patterns are not tied to any specific language. Instead, they describe solutions that can be adapted in any object-oriented language, like Java, C++, or Python. By using design patterns, developers can avoid reinventing the wheel, write cleaner and more organized code, and communicate ideas more effectively with other programmers. Because these patterns have been tested and refined over years of practical use, they help in creating robust and maintainable software. History and significance, Gang of Four. The modern concept of design patterns in software was introduced by four authors: Eric Gamma, Richard Helm, Ralph Johnson, and John Vlasides. Together, they are known as the Gang of Four. In 1994, they published a landmark book titled Design Patterns: Elements of Reusable Object-Oriented Software. This book introduced 23 foundational design patterns divided into three main categories: creational, structural, and behavioral. These patterns became the standard reference for object-oriented design and influenced how developers think about building software systems. Even decades later, GoF patterns are still widely taught, used in interviews, and embedded in modern frameworks and libraries. Understanding these patterns is a key step for anyone aiming to work in professional software development. Categories of design patterns. Design patterns are grouped into three main categories. These are creational patterns, structural patterns, and behavioral patterns. Let's begin with a quick overview of each one. Creational patterns focus on how objects are created. They help make the system independent of how objects are constructed, composed, or represented. These patterns are useful when you need flexible or controlled object creation. Structural patterns deal with how classes and objects are composed or arranged. They help form larger structures while keeping code flexible and maintainable. Behavioral patterns are concerned with how objects interact and communicate with each other. They help in defining responsibilities and flow of control in complex systems. On the next page, we'll take a closer look at examples from each category. Categories of design patterns. Design patterns are grouped into three main categories. These are creational patterns, structural patterns, and behavioral patterns. Let's begin with a quick overview of each one. Creational patterns focus on how objects are created. They help make the system independent of how objects are constructed, composed, or represented. These patterns are useful when you need flexible or controlled object creation. Structural patterns deal with how classes and objects are composed or arranged. They help form larger structures while keeping code flexible and maintainable. Behavioral patterns are concerned with how objects interact and communicate with each other. They help in defining responsibilities and flow of control in complex systems. On the next page, we'll take a closer look at examples from each category. Categories of design patterns. Now let's look at examples from each category of design patterns. Creational patterns include the Singleton pattern, used to ensure only one instance of a class exists. The factory method, which provides a way to create objects without specifying the exact class. And the builder pattern, which separates object construction from its representation. Structural patterns include the adapter pattern, which allows classes with incompatible interfaces to work together. The Composite pattern, which treats individual objects and groups of objects uniformly. And the Decorator pattern, which adds behavior to objects dynamically. Behavioral patterns include the Observer pattern, used for event-driven programming, the Strategy pattern, which lets you choose behavior at runtime, and the Command pattern, which encapsulates a request as an object. In upcoming chapters, we'll study many of these patterns in depth with real examples. Benefits of using design patterns. Using design patterns offers many practical benefits for software developers and teams. First, patterns provide proven and tested solutions to common design problems. Instead of reinventing the wheel, you can rely on industry-accepted approaches. Second, patterns improve code readability. When you use a known pattern, other developers can understand your code structure more easily. This also makes the system easier to maintain and extend. Third, patterns encourage code reuse. By following these reusable templates, you avoid duplication, and your code becomes more organized and efficient. Another benefit is clear communication. When developers use names like Observer pattern or Factory pattern, they instantly convey the design approach without needing long explanations. Design patterns also help create flexible and scalable software architectures, which can evolve with changing requirements. Finally, patterns speed up the design process. They provide a starting point for solving design problems, saving time during planning and development. Overall, design patterns are essential tools for writing professional, reliable, and clean code. When not to use design patterns. While design patterns are powerful tools, it's important to know when not to use them. First, avoid using patterns for simple problems. Adding patterns where they aren't needed can overcomplicate your code. Design patterns are abstractions, and like all abstractions, they add extra layers. If the problem is already clear and easy to solve, introducing a pattern may make it harder to understand and maintain. Also, patterns are not a shortcut to writing good code. They are not a replacement for understanding core programming principles like object-oriented design, clean code, and solid architecture. You should also never force a pattern into your design. Just because a pattern exists doesn't mean it's the right choice for your situation. Good design focuses on clarity and simplicity first. If a pattern genuinely helps solve a real problem and adds value, use it. If not, it's better to stick with a simpler solution. In short, use design patterns thoughtfully, and only when they bring clear benefits. Creational patterns. Singleton, one instance for global use. The Singleton pattern ensures that a class has only one instance throughout the entire application. It also provides a global access point to that instance. This means no matter where you are in the code, you can get the same object. Singletons are useful when you need to share a single resource, such as a configuration manager, a logging system, or a database connection. The pattern makes sure that the class controls the creation of its own instance, so that no other copies can be made accidentally. But while Singleton can be helpful, overusing it can lead to hidden dependencies, so it should be used only when necessary. Now let's look at an example of Singleton in Python. In this example, we define a class named Singleton. We want to make sure that only one object of this class can ever exist. Let's walk through it step by step. First, we define a class-level variable called _instance. This variable is shared across all instances of the class. It will store the one and only Singleton object. Next, we override the special method called double_new. The new method is a built-in method in Python that is called before the constructor, and it's responsible for creating the object itself. Inside the new method, we use CLS, which refers to the class itself, not an instance. This allows us to work with class variables like CLS._instance. We check if CLS._instance is none. That means the object hasn't been created yet. If so, we print creating new instance, and then we call super.new, which invokes the parent class's object creation method. We pass CLS to it so that the correct class is instantiated. Then we store the result in CLS._instance. If the instance already exists, we simply return it. Outside the class, we create two objects, S1 and S2. Then we print S1 is S2 to check if they point to the same object. The output is true, because both S1 and S2 refer to the same Singleton instance. This pattern is often used for shared global resources. For example, you might use a Singleton for a configuration manager that loads settings once, or for a logger, so every part of your application logs to the same place. It can also manage a single database connection that should not be duplicated. By controlling object creation, the Singleton pattern helps keep your software efficient and consistent. Factory method. Interface for creating objects. Subclass decides. The factory method pattern defines an interface for creating objects, but lets the subclasses decide which class to instantiate. This pattern is useful when the code that uses an object should not depend on the exact class of that object. Instead, object creation is delegated to a method, usually defined in a base class and overridden by subclasses. This helps keep your code flexible and loosely coupled because the client code works with the interface, not the specific implementation. Factory method is commonly used in frameworks and plugin systems where object types may vary, but the interface to use them stays the same. Now, let's look at a Python example to understand how the factory method pattern works. Let's walk through this example of the factory method pattern in Python. We start by defining an abstract base class called button using the ABC module. It declares a method called render, which must be implemented by all subclasses. Then, we define two concrete classes, Windows button, which returns the string rendering a Windows button, and Linux button, which returns rendering a Linux button. Next, we define another abstract class called dialog. This is the creator class. It defines an abstract method called createButton, but it also has a concrete method called renderWindow. This method uses createButton to get a button object and then calls its render method. The key point is this: renderWindow uses the product interface, but it doesn't know which specific class is being used. That decision is deferred to the createButton method, which is implemented in the subclasses. We then define two subclasses of dialog. Windows dialog returns a Windows button, and Linux dialog returns a Linux button. Finally, in the client code, we first create a Windows dialog and call renderWindow. It prints rendering a Windows button. Then, we switch to a Linux dialog and call renderWindow again. This time it prints rendering a Linux button. The factory method pattern allows us to write code that is independent of the specific product classes, while still being able to work with different types of products. This is especially useful in applications where the object type might change at runtime, such as cross-platform interfaces, plugin loaders, or theme-based UI elements. Abstract factory, group of related objects. The abstract factory pattern is used to create families of related objects without specifying their concrete classes. Unlike the factory method, which creates one type of product, the abstract factory creates multiple related products, for example, a button and a checkbox that belong to the same theme or platform. The key idea is that all the created objects are meant to work together. This ensures consistency across the components and makes the system easier to maintain. You use this pattern when your code needs to work with various sets of objects that should be interchangeable as a group. This pattern is common in graphical user interface toolkits and cross-platform applications, where you might need different versions of widgets for Windows, Mac, or Linux. But all widgets for a single platform must be visually and behaviorally consistent. Let's now look at a Python example that shows how the abstract factory pattern works. In this Python example, we implement the abstract factory pattern to create a consistent set of buttons and checkboxes for different platforms. We start by defining two abstract product classes, button and checkbox, each with a render method. These represent the product interfaces. Next, we create concrete product classes for Windows and Linux, Windows button and Windows checkbox, as well as Linux button and Linux checkbox. Each class implements the render method, returning a platform-specific message. Now comes the core part, the abstract factory called GUI factory. It declares two methods, create button and create checkbox. Concrete factories must implement these methods. We then define Windows factory and Linux factory, each responsible for creating button and checkbox objects for their respective platforms. Finally, in the client code, we define a function called render UI. This function takes a factory object, creates a button and a checkbox from it, and prints their rendered output. When we call render UI with Windows factory, it prints Windows button and Windows checkbox. When we switch to Linux factory, we get Linux button and Linux checkbox. This pattern allows us to switch the entire set of related components just by changing the factory we use, without touching the client code at all. The abstract factory pattern helps maintain consistency, supports scalability, and keeps code loosely coupled, especially in systems that support multiple themes or platforms. Builder. Step-by-step object construction. The builder pattern is used to create complex objects step by step. It separates how an object is constructed from how it is represented. This allows the same building process to create different representations of an object. This pattern is especially helpful when you have a class with many optional parameters or when you want to construct an object in multiple steps, rather than all at once. Instead of passing a long list of arguments to a constructor, the builder pattern lets you gradually set each part of the object and then assemble it when you're done. The builder pattern is commonly used in parsers, user interface builders, and document generation, where objects can have many customizable parts that need to be assembled in a flexible way. Now let's see how the builder pattern works in Python with a practical example. In this example, we use the builder pattern to create computer objects with different configurations. We begin by defining a class called computer. It has three attributes: CPU, RAM, and storage. The string method returns a readable summary of the computer's parts. Next, we define a builder class called computer builder. In the constructor, we initialize a new computer object and store it as self.computer. We then create setter methods like setCPU, setRAM, and setStorage. Each method updates one part of the computer and then returns self. Returning self allows us to chain the method calls so we can build the object fluently. Finally, the build method returns the completed computer object. We also define a director class, which uses a builder to create predefined configurations. It has methods like build gaming PC and build office PC, each of which calls the builder's setters and returns the final result. In the client code, we create a computer builder, pass it to a director, and then build a gaming PC and an office PC using the director's methods. Each print statement shows the final configuration of the computer. This demonstrates how the same building process can produce different results. The builder pattern helps simplify object creation, especially when the object has many optional parts or a complex construction process. Prototype, clone existing objects. The prototype pattern is used to create new objects by cloning existing ones, instead of creating them from scratch. This is useful when object creation is expensive or time-consuming. For example, when it involves many configurations or database lookups. By copying an existing object, we can create a new one with the same structure and data, while still being able to modify the clone if needed. Python supports cloning through the copy module, which provides two options: shallow copy and deep copy. A shallow copy duplicates the outer object but keeps references to the same inner objects. A deep copy duplicates both the outer object and any nested objects inside it. This pattern is especially helpful in performance-sensitive systems like game engines. Data models or configuration systems where many similar objects need to be created quickly. Let's look at a Python example using the prototype pattern. Let's walk through a proper implementation of the prototype pattern. We start by creating an abstract base class called prototype. It defines one abstract method, clone, which every subclass must implement. This provides a standard interface for cloning objects. Next, we define a class called document, which inherits from the prototype interface. The constructor takes 3 arguments: title, content, and metadata. The metadata is a dictionary that can hold details like author and version. The key part of this class is the clone method. Instead of using the copy module directly from the outside, we encapsulate the copying behavior inside the class itself. Here, we use deep copy to make sure we get a full clone, including nested structures like the metadata dictionary. This makes the object self-cloning, which is a core feature of the prototype pattern. In the client code, we create an original document object. We then call clone to create 2 separate copies. In the first clone, we change the version number. In the second clone, we change the author. When we print the original and the 2 clones, you can see that each one maintains its own independent state. The original remains unchanged, and each clone has its own updated metadata. This version follows the true prototype design pattern, where the clone method is defined as part of the class interface, and object creation logic can be reused or extended in subclasses. The prototype pattern is especially useful in configuration systems, document editors, games, and any application where you frequently create similar objects with small variations without me starting the whole construction process every time. Let's review the creational design patterns using this table. Each pattern solves the problem of how objects are created, especially in complex, dynamic, or large-scale systems. First, the Singleton pattern ensures that a class has only one instance and provides a global point of access to it. In Python, this is usually done by overriding the new method and storing a single instance in a class-level variable like cls._instance. You'll find singletons used in configuration managers, loggers, and database connections. The factory method pattern defines an interface for creating objects, but allows subclasses to decide which class to instantiate. In code, you define a factory method that returns a subclass instance. This is useful in UI frameworks, plugin loaders, or document creation tools. The abstract factory pattern creates families of related or dependent objects without specifying their concrete classes. You typically implement a factory of factories, where one abstract factory returns multiple related products. It's used in systems with themable components, GUI toolkits, or cross-platform environments. The builder pattern separates the construction of a complex object from its representation. The builder provides step-by-step methods that can be chained together, making it ideal for constructing HTML documents, reports, or nested objects. The prototype pattern creates new objects by cloning existing ones. Instead of using constructors, it uses the clone method often implemented using Python's copy module. Prototypes are commonly used in game development, undo systems, or template-based object creation. Adapter. Convert interface of a class into another. The adapter pattern allows two incompatible interfaces to work together. In software projects, we often encounter existing classes or external libraries that don't match the interfaces expected by our current codebase. Instead of rewriting the old or third-party class, we use an adapter class to wrap it with a new interface. This way, the client code can use the standard interface it expects, while the adapter takes care of translating calls to the underlying class. The adapter pattern is especially useful when integrating legacy systems, refactoring, or using external libraries with different designs. It also promotes reusability by keeping the original class unchanged and separating the concerns between old and new components. Let's now walk through a Python example that demonstrates this clearly. We begin with an existing class called oldPrinter. It has a method named print_text, which takes a message and returns a string. However, our client code expects to use a standard interface called newPrinterInterface, which defines a method named display. Because the method names don't match, the oldPrinter class is incompatible with the client code directly. To solve this, we create an adapter class called printerAdapter. It implements the newPrinterInterface and takes an oldPrinter object as input. Inside the display method, it simply calls printText on the oldPrinter. This allows the adapter to translate the expected interface into the old one. The client code defines a function that works with any object implementing the new printer interface. It calls the display method and prints the result. We then create an instance of oldPrinter, wrap it with printerAdapter, and pass it to the client function. The output is oldPrinter:"hello world," which means the adapter worked and the client was able to use the legacy class without knowing anything about it. This is the core benefit of the adapter pattern, making old or external code usable in modern systems without touching the original source or rewriting your app. Bridge. Separate abstraction from implementation. The bridge pattern is used to decouple an abstraction from its implementation, so that both can evolve independently. In traditional design, when you want to extend functionality, you might use inheritance, for example, subclassing a window class for each operating system, but this approach creates a tight coupling and quickly leads to an explosion of subclasses when you need to support more combinations. The bridge pattern solves this by using composition instead of inheritance. It separates the high-level abstraction from the low-level implementation and links them together using a reference, or a bridge. This is useful when building cross-platform applications, graphical user interfaces, or any system where you want to extend behavior on both sides independently. Let's walk through a Python example that shows how this works. This is a Python example of the bridge design pattern where we separate the abstraction of a shape from its rendering logic. We start with an abstract class called renderer, which defines the method renderCircle. This is the implementation interface. Then we define two concrete renderers, vector renderer, which simulates rendering using vector graphics, and raster renderer, which simulates rendering using raster graphics. Now for the abstraction side, we define an abstract class called shape. It takes a renderer object as a constructor parameter, which allows us to plug in any rendering strategy we want. This is where the bridge is formed, through composition. As you know, composition in classes is a type of relationship where one class contains an instance of another class as a part of its definition. So abstract class shape has a renderer which is also abstract. We then define a refined abstraction called circle, which inherits from shape and stores the circle's radius. In the draw method, the circle calls the render circle method on the renderer it was given, whether vector or raster. In the client code, we create two renderers, one vector and one raster. We then create two circle objects. One uses the vector renderer with a radius of 5, and the other uses the raster renderer with a radius of 10. Calling draw on each prints out different rendering styles, but the circle abstraction doesn't care how the rendering is done. This pattern lets you change or extend the shape hierarchy and the rendering implementation separately. The bridge pattern helps keep your code scalable, modular, and platform independent by cleanly separating responsibilities across different dimensions. Composite, tree structures for hierarchies. The composite pattern lets us treat individual objects and groups of objects the same way. It is ideal for hierarchical structures like trees, where objects can be composed of other objects of the same type. For example, in a file system, a folder contains files, but it can also contain other folders, and you want to treat them all uniformly when displaying, moving, or deleting. The composite pattern solves this by building a structure of components, some of which are leaf nodes, like a file, and others are composite nodes, like a folder that contains children. This pattern relies on composition to build recursive relationships. As you know, composition in classes is a type of relationship where one class contains an instance of another class as a part of its definition. So in this pattern, a composite node has a list of other components, which may include both leaves and other composites. This allows you to write code that handles all elements the same way, whether it's a single item or a whole group. Let's look at a Python example that demonstrates this concept. Here is a full implementation of the composite design pattern in Python. We start with an abstract base class named graphic. It defines a method called draw, which every shape must implement. We then define two leaf classes, circle and square. Each of them implements the draw method to print its shape. Next, we define a composite class called drawing. It also inherits from graphic, so it follows the same interface. Inside the drawing class, we use a list called children to store shapes. This is an example of composition, where a class contains other objects of the same interface. The drawing object has a list of graphic objects, which could be circles, squares, or even other drawings. The add method allows us to insert new components into the drawing. The remove method lets us delete components. The draw method simply loops over all children and calls draw on each of them. This is how the drawing class delegates work to its parts, whether they are leaves or other composites. In the client code, we create some shapes, 2 circles and 1 square. We build a group that contains 1 circle and 1 square. Then we build a nested group, which contains another circle and the previous group. Finally, we call draw on the nested group. The output prints drawing a circle, drawing a circle, drawing a square. Even though some of these were inside groups and subgroups, the client didn't have to care. That's the power of the composite pattern, treating individual items and groups in the same way through a uniform interface and recursive composition. Decorator. Add responsibilities dynamically. The decorator pattern allows you to add new behavior to objects dynamically without changing their original code. This follows the open-closed principle, which means classes should be open for extension but closed for modification. Instead of modifying the original class, we wrap it in a decorator class that adds functionality before or after calling the original method. This avoids creating many subclasses for every possible combination of features. The decorator uses composition. It contains an instance of the class it decorates. And it uses delegation, meaning it calls the methods of the original object from inside its own methods. This pattern is common in logging, input validation, access control, and formatting. Let's look at a full Python example that shows how decorators work. In this example, we demonstrate the decorator pattern using a simple notification system. First, we define an abstract base class called notifier. It defines the method send, which takes a message string. Then we define a concrete class called email notifier. It implements the send method and prints the message as an email. Now comes the core of the pattern, the decorator class. We create a base decorator called notifier decorator. It also implements the notifier interface, but instead of sending messages itself, it contains another notifier instance using composition. This wrapped instance is passed through the constructor. The base decorator simply delegates the call to the wrapped object send method. Then we define two concrete decorators, SMS decorator, which adds logic to send an SMS after the wrapped notifier sends its message. Slack decorator, which adds logic to send a Slack message the same way. In the client code, we build the stack in layers. First, we create an email notifier. Then we wrap it with an SMS decorator. And finally, wrap that with a Slack decorator. When we call send, the message is passed through each layer. The email is sent first. Then the SMS is sent. And finally, the Slack message is sent. This structure lets us add or remove functionality at runtime without modifying any of the original classes. Each decorator class is responsible for just one additional behavior, keeping the system modular and flexible. This pattern is especially helpful when you want to avoid subclassing for every combination of features, and instead prefer to build functionality using wrappers. Facade simplified interface to a subsystem. The Facade pattern provides a simplified interface to a larger and more complex system. Instead of exposing all the methods and details of many subsystems to the client, the Facade hides that complexity and exposes just what the client needs. It acts like a wrapper or a front door, coordinating multiple parts under the hood. This promotes loose coupling because the client no longer needs to know how each subsystem works. It just talks to the Facade. This pattern is common in APIs, frameworks, toolkits, and even home entertainment systems. Think about pressing one button on a remote that turns on the TV, sets the input, and powers on the speakers. You are using a Facade. Let's look at a real Python example of how a Facade works. This Python code demonstrates the Facade design pattern using a simplified example of starting a computer. We begin with three subsystems: CPU, which can freeze, jump to an address, and execute instructions; memory, which can load data into a given address; hard drive, which reads data from a sector. Each of these classes has low-level operations that need to be called in a specific order to start the system. Then we create a computer Facade class. It holds instances of the CPU, memory, and hard drive using composition. Inside the start method, it coordinates their actions. It first freezes the CPU, then reads data from the hard drive, loads it into memory, jumps to the correct memory location, and finally executes instructions. All of that logic is now hidden from the client. The client code just creates a computer Facade object and calls start. It doesn't need to know which subsystem does what. It just gets the behavior it wants. This shows how a Facade simplifies usage, keeps the code clean, and separates concerns between the user and the system internals. Flyweight. Efficient sharing of large numbers of objects. The Flyweight pattern is used to reduce memory usage when your application needs to create a very large number of similar objects. The core idea is to share common data between objects instead of duplicating it in every instance. Flyweight objects are divided into two types of data: intrinsic data, which is shared and stored in the Flyweight object; extrinsic data, which is unique to each use case and passed in when needed. This pattern is extremely useful in memory-sensitive applications like graphical user interfaces, where many identical icons are displayed, games, where you may have hundreds of similar trees or bullets, text editors, where every character can be a flyweight. All shared flyweights are usually managed by a central factory, which ensures you reuse existing objects instead of creating new ones. Let's see how the flyweight pattern works in Python. This example demonstrates the flyweight pattern using characters in a simple text renderer. We define a character class, which acts as our flyweight. It stores intrinsic data like the symbol and the font. These are shared between all characters with the same configuration. The method render takes in the extrinsic data, which is the character's position on screen. This is passed in from the outside. Next, we have the character factory class. It uses a dictionary to store existing character objects. In the client code, we define a list of characters in a document. Each entry includes the character, the font, and its position. We loop through each item, ask the factory for the matching character object, and call the render method with the position. Even though 5 characters are displayed, only unique combinations of symbol and font are created. This saves memory, especially in documents with thousands of characters. This example shows how the flyweight pattern reduces duplication, optimizes memory, and separates shared data from instance-specific data. Proxy, control access to an object. The proxy pattern provides a substitute or placeholder for another object. It's used when direct access to the real object is not desirable or possible. The proxy has the same interface as the original object, so the client can use it just like the real thing. A proxy can do many things before or after forwarding a request, such as logging access, delaying object creation, controlling permissions, caching results, or communicating with a remote service. There are several common types of proxies. Virtual proxies delay expensive object creation until needed. Protection proxies check access rights before forwarding. Remote proxies stand in for objects in another machine or network. Caching proxies store and return previous results to avoid repeated computation. Let's now look at a real-world example in Python using a virtual proxy to delay loading a heavy object until it's actually needed. We start with a class named image. It simulates a heavy object, for example, loading a photo from disk. The constructor prints a message and stores the file name. The display method simply prints the file name. Next, we define the image proxy class. It accepts the same input, the file name, but it doesn't load the actual image right away. Instead, it sets the _image attribute to none. When the client calls display, the proxy checks whether the real image has been created. If not, it prints a message, creates the image object, and then forwards the display call to it. If the image is already loaded, it simply prints a message and forwards the call again. In the client code, we create an image proxy object. No image is loaded at this point. When we call display, the proxy loads the image and then displays it. On the second call, it reuses the loaded image. No extra work needed. This demonstrates how a proxy can control access, perform lazy loading, and manage expensive resources efficiently without changing the client code. Let's review all the structural design patterns we've covered side by side. This table compares the main idea of each pattern, how it's implemented in code, and where it's used in real-world software development. The adapter pattern lets incompatible interfaces work together. In code, it wraps an old class and translates method calls. It's great for integrating legacy systems or connecting external APIs. The bridge pattern separates the abstraction from its implementation. It uses composition to decouple layers of code. This is useful in cross-platform tools or GUI frameworks. The composite pattern allows you to treat individual objects and groups of objects the same way. It's often implemented with recursive structures and a shared interface. You'll see it in file systems, hierarchical menus, and scene graphs. The Decorator pattern lets you add new responsibilities to objects dynamically. It's implemented by wrapping objects in other classes that follow the same interface. Thanks for watching.